Before mechanical excavation, all digging operations relied on manual labor, animals, and simple hand tools. Large infrastructure projects such as canals, harbors, and railway embankments required thousands of workers and often took years to complete. As industrialization accelerated during the early 19th century, engineers faced increasing pressure to reduce project duration and labor requirements. A machine capable of continuously excavating and loading material became an engineering necessity. The first practical excavating machine was patented in 1835 by William Smith Otis. Known as the steam shovel, it marked the beginning of mechanized earthmoving. Unlike modern excavators, steam shovels operated through a combination of steam engines, wire ropes, drums, pulleys, and mechanical clutches. Steam generated inside a boiler powered reciprocating pistons, which rotated winches to control bucket movement. At the heart of the steam shovel was a fire tube boiler. Coal or wood was burned inside a furnace, heating water stored within the boiler shell and producing high-pressure steam. The boiler typically operated at pressures between 80 and 120 pounds per square inch, or about 5.5 to 8 bars. The steam was then directed into one or more double-acting reciprocating cylinders. Steam entered alternating sides of the piston, causing it to move back and forth in a linear motion. A connecting rod attached to a crankshaft converted this reciprocating movement into continuous rotational motion. This rotational power was transmitted through shafts, gears, and drive mechanisms to a series of independently controlled winches located throughout the machine. Each winch was responsible for a specific operation. The hoist drum raised and lowered the dipper handle. The crowd drum pushed the bucket into the soil and retracted it after digging. The swing drum rotated the upper structure of the excavator, while the propelling drum moved the entire machine along its railway tracks. The operator controlled these functions using manually operated friction clutches and band brakes, engaging or disengaging each mechanism as needed during the digging cycle. The bucket was rigidly attached to a dipper handle, which was supported by a boom positioned at an angle of approximately 45 to 60 degrees. The excavation process consisted of 4 distinct stages. The first stage was penetration. During this stage, the crowd mechanism pushed the bucket forward, forcing its teeth into the ground and breaking the soil. The second stage was filling. As the bucket continued to move through the material, soil entered through the open front face and gradually filled the bucket cavity. The third stage was hoisting. Once the bucket was full, wire ropes wrapped around the hoist drum lifted the loaded bucket upward. The final stage was dumping. A latch mechanism released the bucket door, allowing the excavated material to fall into a rail wagon, truck, or spoil pile. Depending on the type of material being excavated, a complete digging cycle typically required between 30 and 60 seconds. For example, consider a steam shovel equipped with a bucket capacity of 0.75 cubic meters and operating with a cycle time of 45 seconds. In 1 hour, the machine could theoretically complete about 80 digging cycles. Multiplying 80 cycles by a bucket capacity of 0.75 cubic meters results in a theoretical production rate of approximately 60 cubic meters per hour. However, actual productivity was usually lower. Factors such as operator fatigue, periodic boiler maintenance, repositioning of the machine along the tracks, and variations in soil or rock properties reduced the effective excavation rate under real working conditions. Early steam shovels were constructed mainly from riveted wrought iron and cast iron components. Steel production technology was still developing during the mid-19th century, so engineers relied heavily on these materials to provide the strength and durability needed for demanding excavation work. A typical steam shovel weighed between 12 and 18 tons. The steam engine produced between 40 and 100 horsepower, depending on the machine size and application. Bucket capacities generally ranged from 0.5 to 1 cubic meter. These machines were capable of digging to depths of 4 to 6 meters and could dump excavated material at heights between 3 and 5 meters, making them suitable for loading rail wagons positioned alongside the machine. Despite their revolutionary impact, steam shovels suffered from several inherent limitations that prevented them from becoming truly efficient and versatile earthmoving machines. One of the biggest drawbacks was their low thermal efficiency. Steam engines converted only about 5 to 8% of the fuel's chemical energy into useful mechanical work. In other words, more than 90% of the energy produced by burning coal was lost before it could be used for digging. Large amounts of heat escaped through radiation from the boiler shell, exhaust steam released into the atmosphere, condensation within the steam pipes, and incomplete combustion inside the furnace. As a result, Fuel consumption was extremely high, often exceeding 200 kilograms of coal during a single operating shift. Maintenance was another major challenge. Keeping a steam shovel running continuously required an entire crew. A boiler operator was responsible for maintaining steam pressure and water levels. A machine operator controlled the digging functions. A fireman fed coal into the furnace and removed ash deposits, while a lubrication technician ensured that gears, bearings, and moving parts remained properly lubricated. Daily maintenance activities were extensive. Boiler tubes had to be cleaned regularly to remove soot and scale buildup. Ash residues needed to be removed from the furnace. Water tanks had to be replenished frequently. Wire rope tensions required adjustment, worn brake linings had to be replaced, and bearings and gears demanded constant lubrication. Safety was also a serious concern. If water levels inside the boiler dropped too low, the overheated metal surfaces could weaken and rupture, potentially causing a catastrophic boiler explosion. Another significant limitation was the lack of precise control. Bucket movements depended entirely on the operator's skill in engaging and disengaging friction clutches while applying band brakes. Unlike modern hydraulic systems that allow smooth proportional control, steam shovels were prone to sudden accelerations, swinging motions, and oscillations of the bucket. Positioning accuracy was poor, and coordinating multiple functions at the same time was extremely difficult. Simultaneous digging, hoisting, and swinging operations required considerable experience and often reduced overall productivity. Despite these shortcomings, steam shovels transformed the construction industry and became symbols of industrial progress by the end of the 19th century. Manufacturers such as Marion, Bucyrus, and Ruston and Hornsby developed progressively larger and more capable machines. Some were able to excavate several hundred cubic meters of material per day, far surpassing the output of manual labor. These machines played a crucial role in the construction of transcontinental railways, the expansion of coal and iron ore mines, harbor dredging projects, large-scale canal excavations, and the development of early urban infrastructure.